Hello everyone, I hope you are doing great. In this tutorial video, I would like to talk about the part 2 of solar cell simulation with Lumerical FDTD. In part 1, I talked about the optical part of 3D perovskite solar cell that we could simulate generation rate, and but we had a problem with the short current density, short circuit current density, and now I would like to correct this issue and then continue to couple the device with the FSP. I mean FDTD with a device. We can see here with maybe DGTD. This is for a device, and you can see we can simply charge, heat, DGTD, FEM, MQL, and it's depend on our simulation. Okay, excuse me, I mean FEEM. FEM, it's let me show you. It's for charge and semiconductor properties simulation. Okay, before I start this section, I just want to continue to correct the issue of current density. I look at this in previous simulation. We had solar generation, and when I just calculate the JSC, we couldn't see any calculated result. And let us check the model. This model contains of AU, HTL, perovskite, ETL, and FTO glass. You can see here we have FDTD. This FDTD region is the region of the simulation. I can just turn it, and you can see the region of the simulation is from the bottom to top. Maybe it's very very upper and lower from the basic geometry, and I just change it, the y minimum from, for example, 0.1 to maybe 1. You can see it is changed. Let me bring it lower. Nice. And maybe to 0.9, and I apply, or let me add it to 1. Nice. It is just regional simulation, but as we know, the mesh is defined on the inside of geometry. Okay, and here we have a monitor. The monitor is in the below, but the light illuminated from the top, and we need to bring up the monitor. I bring it up to, for example, 1.1 micrometer, or maybe 1.50. Nice. This is our monitor, and the monitor must be upper than the source. Let me check the source. Oh, the source is outside the geometry, and this is why the model couldn't work properly. Let me change the the side of this source to see what we need to do for the final simulation. Okay, I just edit the object. I bring the geometry. Maybe it's better from the minus 0.5, for example, because the x minimum and maximum from minus 0.1 to plus 0.1, and we can just change it to lower. Okay, and the y, it must be 1.1, maybe it's good. Okay, now we can see the monitor is the upper, and let me choose a bigger monitor. The x, it's better from minus 2, I can see that, and also I bring it upper from, for example, 1.2. okay, and the source I bring it to 1.15. nice. Let me correct the figure. The z direction, look at this is the good. The source is lower than the monitor is upper than that, and it is okay. Now I think I can just file save as. I just save it in any folder, but consider this fact, it's better use a folder in drive D or E, not just C, because C is the drive of Windows that your computation will process here. But this is, for example, I just save it here. I rename it as PSK, and I rename it to PSK bold, PSK. Nice, and I saved. Now I can just check the mesh another time. I just use the override Y mesh. The Y important because the illumination in Y direction, and geometry I just choose the same as the default of the geometry. And now I can run it again to see what the result will be. Okay, now I can go back to solar generation and I can calculate it. Oh, it's not good yet. Let me check the code of solar generation. I can remove it. Also, let me layout. I will remove this, and before removing, I just go to more choices. Okay, I remove this and I add the optoelectronic solar generation rate. Okay, now it's better use an object that inside the geometry. I choose, for example, 0.5 micrometer, and Y span is 1, and Z span is, X span is maybe 0.1, 0.1. I apply it. For seeing the better result, I just halo it or wireframe it. You can see the black cubic is a generation rate region that we want. Okay, now we can simulate. I just Control S to save it. Look at this, for saving the file, just you can Control plus S, just push it, and I run it again. Nice. For solar generation, I just calculate JSC. And now you can see the none. We must check another time everything to see what happened for our simulation. Okay, I just recheck the source again. Maybe our source is not good. It must y-axis backward, it's okay. The geometry, it's okay. Beam options. Let me check the switch to layout model and set the global source setting, frequency. Okay, eliminate discontinuous. Okay, all of the settings are okay now. And I just use relative coordinate. It's okay. Nice. Plane wave, block, predict. It's okay. But we can do other boundary port, but I just choose block. And for monitor, the monitor is good, but I check it again. We have a source limit is okay, and frequency is okay, and simulation is we can choose all type or 2D Z normal also. Let me check this. Global monitor, also source limit. Okay, I run again. Maybe all must be 2D Z normal. Let me check it. No, it doesn't matter for source. Excuse me, for monitor. Maybe all, it's better. Okay. And FDTD, oh, it's okay. The simulation region is not good. Look at this, the FDTD region. Maybe we can bring it upper. Let me bring this upper. For example, from 0.3. Nice. And run it again. Nice. And now just calculate. The JSC is also the same. We must recheck the data. AU is okay. The HTL also. Let me use another data, for example, titanium. Okay, Perovskite. It's okay. You can modify any of this material. It depends on you. And I just talked about it in previous video. Okay, here also I choose SiO2 for glass. Nice. And I just run it. Let me save it. Okay. And I run it again. Nice. Still have problem. JC is NaN. It means not applicable. Oh, let me check the field inside of this. We can check the setup, the X. Maybe the lens must be varied. I just check the 0.5. Okay. And also the Y span, I just choose a lower values. Nice. And let me check the script. There is no errors in a script, and it's okay. And also in variables and in setup script also everything is okay. And let me check the mesh. Let me check the override on any direction and run it again. It is better to modify step by step. I mean, each parameter you change it, then it's better run it to see what the result will be, and then continue for changing other parameters. Okay. I just bring this. Okay. I bring it down. Nice. And the monitor. Oh, maybe monitor and source must be aligned. I choose linear X. Maybe 2D Z normal. Okay. No, these are not aligned. It's weird. Okay, let me bring this one. Oh, maybe FCT must be higher than this. Y must be 1.2 from 0. Apply it. Okay, it's better now. And the monitor here, the source. Now it's aligned. Let me save it again and rerun it. Okay, okay, now you can see the JSC is 295 ampere per meter. Let me show you per square meter. I show you in paint. It will be 29.5 milliamp per square centimeter. Look at this. This is 295 amps per square meter. That is equal to, let me convert this. It can be milliamp. 10 to the power of 3 to 10 to the power of -4, and this is a squared centimeter. And when applied this, it will be converted to 29.5 milliamp per centimeter. Okay, and also the G, it can be calculated, and G export also can be calculated, and we can visualize this. We can see the generation rate, and it is okay. This generation rate is okay, and look at this in the code. We can see G export file name as the value of G. Let me go to the perovskite file. You can see the GMAT and QMAT that is exported from this, and we have a generation rate that we can import for the device simulation, for IV curve, for band structures and everything that is related to electrical part. Okay, I just save it and I close it. Now I can open the charge, the mode, you know, all of these are the same. You can see the triangle logo for this, or the square, two parallel line crossed logo here. And it doesn't matter when I open the charge or open FEEM, it doesn't matter. Okay, let me open the charge. Okay, when I open the charge, you can see the charge, material, geometry, boundary condition, everything. You can see everything here in view, in design, in file, and I can save this file, save as, let me back to perovskite file. I just, it's better use the same name. I just copy this name and I add it for this, and the file extension will be point or .idev. It means device. Yeah, I just save it. Now if I back, I can see psk.idev. Okay, and now I can add different materials, and let me add the material electrical, and look at this. This is the materials. You can add the electrical and thermal, optical, or new material. If I click on electrical and thermal, I can see some default material. I can use, for example, look at this. You can see the properties, for example, electronics, DC permittivity, interpolation, EC value, MNMP, or band gap. You can check everything or every data. For example, you can see the cadmium sulfate, cadmium telluride. I just choose cadmium sulfate as this is just for example. You can modify everything. Okay, you can modify it, and let me cancel it. Okay, now I just add 2 or 3 material. Let me add it. Cadmium sulfate. Okay. Before adding, just let me check that. We can visualize also to see band gap. Look at this. When I create visualization, you can see the band gap versus temperature. Here the temperature does not affect the band gap, for example, and then you can see the 2.56 for all the temperature. It doesn't matter. But also MNMP is the effective electron and hole effective mass. Mobility, it's mu n and mu p for electron and hole mobilities. And this is saturation velocity. It is saturation velocity for hole. This is for electron. This is carrier lifetime for Shockley-Rittal model. This is for electron and this is for hole. This is the optical capture coefficient, and this is the Auger capture coefficient for electron, and this is for hole. Okay, before adding the materials, it's better using a geometry. I choose the same geometry, for example, rectangle. Let me check the properties of either FSP. I use the same structure. In console you can copy and paste, but here we must go back and build it from the first top. Okay, 0.1 minus 2 plus 0.1. Okay, I build AU, edit object, I rename it as AU 0.1, 0.1, and this is from 0 to 0.1. And also this is from -1, -1. And the material, I can add any material I want. I just add it. Let me, okay, you can see the AU. Let me check everything. 0.1, 0.1, and the Y is nice, but we must excuse me, let me check it again. 0.1. Okay, in Y direction. Okay, now I can add another new geometry for HTL, and HTL is 200 nanometer. This is HTL. And 0.1, 0.1, and from 0.1 to 3. Oh, excuse me, maybe. Okay, 0.1. Nice. And we have HTL. It was 200 nanometer. Let me check again. It's okay, 200 nanometer, and Perovskite was 500 nanometer. I can add the Perovskite as PSK. PSK. Okay, 0.1, 0.1, 1, and 1. This was from the 0.3 to 0.8. Okay, and I can just nice. And I add the ETL maybe 100 as I remember, but let me check. Yeah, it is 100 nanometer. I add the ETL from 0.8, 0.9, This is 0.1, 0.1, and also the same for this and this. Okay, and the last one is glass FTO or FTO glass. I can copy the name. It is about 200 nanometers. 0.1, 0.1, 0.1, and this is from 0.9 to 1.1. Okay, nice. And this is the final structure. We can see FTO, ETL, perovskite, HTL, and AU. Nice. We can continue. I can save it at first. Here we have a charge. In charge, we can add the constant doping, diffusion, implant, or import the doping, any doping model. But I choose a constant model. I edit object. I remove it as ETL. And we can start from -1. Excuse me, 0.1 minus to 0.1 plus, and also for this minus 0.1 to 0.1, and y minimum for ETL. We are here. This is from 800 to 900. 800 nanometer to 900. Okay, and we can add it as L, N, and 1E18 maybe. It's better. Nice, I add it. Okay, let me check the simulation region also. You can see 2D by normal, it's okay. Material and geometry. We can consider all geometry. 0.1, 0.1, and also 0.1. And we can see 2D Z normal. It help us, yeah, for maybe it's from 0 to 1.1. Let me apply it to see what the results. Nice, we can see the simulation setup of this region. And also we could add 3D, it doesn't matter, okay. And let me, okay. For charge, I add the ETL. Then now I can add the HTL. Let me add the constant. I rename it as HTL. HTL from minus 0.1, 0.1, and also 0.1 to excuse me, minus 0.1, and the y must be from 0.1 to 0.3. Okay, and the dopant must be P for HTL, and I can choose 1E16. Okay, and also let me check the relative coordinate. Okay, use the relative coordinate. If I choose the domain, oh, okay, all domains. For perovskite, I can consider the intrinsic type. Intrinsic type, there is no need to for N or P, because the N or P type of that must be the same. It means the electron hole must be equal, and there is no need for adding. Okay. And for optical part, I can add optical sources, generation rate. I can edit object X from. I can add the all domains X, for example, 0.2, 0.2, and this is 1.1. And the data, I can browse the data from GMAT, and I load it here, then I apply it. Okay. Nice. We have generation rate now in all device. I can save it. Okay. For electrical, we have two contacts, front and back contact. I add electrical. I added as a, for example, FTO contact or ITO contact. It doesn't matter. FTO. Contact. Okay. We can add it as a steady state single and at voltage 0. But in geometry, we can add it maybe in simulation region for Y minimum. It means the in simulation region or in domain every where that you want, and we can apply it and okay it. Excuse me, FTO must be FTO contact Y minimum. It's okay. Or why it's weird. Maybe we can rename it to F contact. Nice. And excuse me, it must be for Y maximum because the FTO is in the top. I forgot it. I add another electrical. We can add it as AU contact. No, it cannot acceptable. The AU. It shouldn't be a space or a slash here. Okay, maybe a slash is acceptable. Let me check the slash or underline or under. Okay, underline is acceptable, and here I can add domain in simulation region, maybe in Y minimum, and also I can add the sweep range from 0 volt to by interval of 0.2, for example, from 1.1, which is very high. Let me choose a 1. Nice. And you can add the lump impedance or resistance or and force ohmic, or we can use ohmic contact, or if I choose a true, it will be ohmic contact, but if I choose a false, it will be Schottky contact. Okay, I choose for example true for Y minimum, and this is AU contact, and let me recheck this FTO contact. FTO contact. Okay, and I can save it. Now for material, I must add the material, and it is important because we need to add the material for charge simulation. Let me add some of material, for example, CDS. Oh, it's weird. I don't know why that is not added. We can choose add new material. In new material, add electrical properties, thermal, optical. I add the electrical properties. Now we can add, it's okay. It's so weird, but it's okay. We can choose a CDS as ETL. I rename it as ETL, for example. We must check the everything. Now we can rename it. I can change everything. I mean the mobility, effective mass, band gap, recombination rate, tau and tau p, k, and this is the crystal constant, is not important. The work function, that is electron affinity, EC value from X or L direction or a gamma direction. It doesn't matter. These are available in the papers. I just add OK. And also we can rename it, for example, TiO2 or everything. TiO2. And the HDL, maybe we can choose a CDSE, for example, or cadmium telluride, maybe. Cadmium telluride, it's near to perovskite. Let me choose CDSE. Yeah, CDSE is better. I select the CDSE. Nice. I rename it as HDL. HTL, nice. I rename it this as, for example, spirometer. Nice. And I added another new material here, and I add electrical properties from, for example, maybe cadmium telluride is good option. Nice. I just selected. You can change every data. Okay, this is arbitrary and depends on you, and not very hard. Just find the data and rename it. It's okay. I just rename it as PSK, and the new material PSK. Nice. And I add also other new material for AU and glass. Add electrical property, yes. I add the AU. You can see the work function 5.1. I select it. Nice, and I rename it as AU. And the other one is FTO glass. It doesn't matter. I add the new material. Okay, I add electrical property. Oh, excuse me, it was to delete. In new material, I add electrical properties. For example, SiO2, or maybe SNO2, SNO2F. It's okay, I choose SiO2 and I select it. Nice, I just rename it as glass. Nice, I just save it. I go back to geometry and I just link the material with the geometry. Okay, nice. I back to AU. I go to material, I add AU, and I left the other properties. Nice, AU, HTL, I add the HTL properties, material, HTL, and I OK it. Nice, Perovskite, edit material. I go to material, Perovskite, OK, ETL, edit material. ETL, okay, and glass. I go to material and I add the glass. Okay, just I recheck one of them randomly, for example HTL, to see I did correct. It's okay, I did correct. Nice. We add material properties, band gap, electron affinity, and other electrical properties. The optical properties were taken from the FSP file here, and we added and the generation. We add ETL, HTL, concentration or doping, and also contacts were added. And the simulation region was the whole simulation region of the device. And now we can add monitors, for example current. Let me add the current. Nice, we can edit the object. We can have a 3D or 2D monitor, it depends on us. X from 0.1, 0.1, 1 to 1, and this is from 0 to 1.1. And we can see linear X, linear Y, linear Z, or 2D Z normal. It means we just see the simulation regions, and it's okay. Just let's bring it here. Nice. And now we must add the mesh. I add the mesh. Oh, excuse me, let me force quit. Yeah, we must add mesh here. Okay, in view or in design, we can see mesh. We also could add surface recombination for interfaces, but I didn't add. And we can generate charge transport mesh. It's okay. Let me, or here we can add constraint. This is a type of mesh. The constraint is electrical mesh. Can edit object and from point 1 to 1, and this is from 0 to 1.1. Nice. And we can save it. Okay, now I can simulate it just by running. We can also add band structure, electric, charge, you know, everything. But I just add these. And simulation region. It's okay. For also the heat properties, also we can add temperature or heat, and the heat flight convection, all of them will be available. Nice. I just saved the file, Control S, and I run it. I hope it will be run without any problems. Okay, it takes time because okay. Maybe our model is not correct. We must check everything. Maybe mesh and everything we must check it. Okay, let me force quick. Nice. I can go back to mesh. I deleted this. Let me bring mesh by the solver. It is auto mesh by Lumerical. Nice, we can. And now I just run it. to see what the result. And also in charge solver we could change the simulation type. We have a Newton model and Gamel model here, and some settings we can change everything. Okay, it is not run yet. That is heavy model, sometimes hanging. Okay, in charge solver, let us to check the solver. And this is a steady state. We can order transient, and we can change the normal length. It doesn't matter. The minimum edge is 0.1. Maybe it is 0.2. It's very good. For transient, I don't want transient on a small signal. Advanced. Here you can see Gamel. I can use a Newton, for example. I choose a Newton. And Fermi statics, I can enable it. And I left the others. And over here, I just apply it. Let me check the okay, boundary condition. I add, must check everything. Single voltage, steady state, true. High maximum for FTO, yeah. True, okay. By minimum simulation region from 0 to 1.1. Okay, let me add the quality constraint. For mesh, I edit objects. Apply. Let me check the mesh at first, then I run it. Also, we can remove monitor of current. At first, study without monitor, then add the monitor of current or other thing. Nice. Now I just run it. We can see grade, area ID, which you can check in these parts. Here, meshing status finished, and the step and the status is running. It will start another time, but here we can view job details. A conductor was no specified contact properties. Okay, I understand. For squid, yes. Maybe it's because of I understand. We have two contacts, but we define one of them as a glass. Look at this. This is the glass. Let me we name it to FTO glass. Okay, and I delete these. I understand that because it needs to finding the work function, but the glass has no work function, or work function of that is very high, and it's better use FTO like materials. For FTO like, maybe CU. Yes, it is near to, as I know, it is 4.7 electron volt. The work function properties, I just save it. I go back to charge. It is hanging. And I run it again to see if it has error or no error. I hope it runs without any errors. I hope. Sometimes you must work on it because there are many parameters, there are many boundary conditions. You must check everything. Okay, I still have problem. A conductor with no specific contact properties. Okay, let me force quit, yeah, to see what is the problem. Let me check. This is work function, okay. And for AU also. .1, it's okay. And let me check the FTO glass. Yeah. Material, FTO glass, yeah. Material is AU, it's okay. And for FTO contact, if I choose domain, solid is, maybe solid is better. I choose FTO glass, outer surface, it's better, outer surface. And for AU contact, I go to geometry, solid, AU outer surface only, yes. I apply it and I OK it. Control S. Now I just run it again. I hope. No, it's okay. I hope. The mesh is okay now. Okay, now we can see it is running now. The voltage step 0 is completed and we are in 100 millivolt. It depends on your system, as I talked about it. Okay, it's hanging because maybe the mesh is not good, or maybe the contact is not good. We can sweep on maybe on FTO because it's finished. Let me quick save here. And also the sweep range, it's important. You can see everything here, okay? For voltage of 0. Let me show you. We can see everything here. For example, electrostatics and doping. Look at this is doping. And the band structures. Look at this is band structures. And everything, our integrated IQE, ROPT, and other data. Nice. I go back to ITO, and you can see here this is ITO AU. Let me check. We can layout it, and I can check it. IU was the we can range on FTO from 0 to 1 with interval maybe 0.2. Maybe it's good, but let me check it. If we can choose ohmic I just force ohmic contact to false, and AU contact this is single voltage, and I choose a false. Apply and okay it. Nice, and another time I just run it. I hope this time it is run. It will run, I hope. I hope it runs. Nice. Okay. 10 and 20 was okay. 40 is okay. 60 is okay. Oh, now it's better. I just changed the contact of voltage sweeping from AU to FTO, and FTO is the contact that voltage is swept on it. Very good. We have 30% now, 32, 34, 36. I choose 20 millivolt as a step range. You can try on lower values, maybe 1 millivolt or 10 millivolt or 5 millivolt maybe. It depends on your accuracy of your simulation. Sometimes it is important, sometimes it doesn't important, and you can use a coarse step voltage. Okay, you can see we have error on 44 millivolt. I will let you know why this is happened because of the data. I just quit and save. I tell you why. Because I choose arbitrary data. You understand that? It's perovskite I choose a cadmium telluride. For ETL, I choose CDS, and for HTL, I choose CDSC. Okay, this band alignment is not good, and it caused some problem. And you can work on it. I mean, just correct the data. The band gap. Look at this. The band gap of a spiral is about 3 electron volt, as I know, and the electron affinity is about 4, maybe, or maybe about 3. Just correct all of them. Okay. After correcting all of them, you will get a good result. Nice. In charge simulation, we can see everything. We can see contact. Let me visualize contact, current density. We can see the let me remove all of them and just excuse me another time. I just visualized. Nice. I can remove everything here. Look at this. I just remove this one. Okay. Now you can see I and IN, and I remove IN, and you can see IN. This is not good because you can see some mistake was happening. Current density, as I told you, it's because of the band alignment and the electrical properties. Okay, but it is wrong. You can see it's from 0.0 to 0.4. It was wrong, and maybe the shape was formed, and it is okay. We can visualize other data. Also, maybe here we can see P, IQE, and everything. You can see a curve here that is hoping for IV. Nice. Electrostatic also, I can visualize it. Nice. If I just change the data, let me change the data. Maybe I must go to my CV. Just let me go to my CV. My papers. Okay, in my papers, maybe I find the data for the simulation. Oh, some of them are not open. It's so bad. Nice. No, this is not. This is good. I just try to use this data. It's better. Let me check this data. Yes. Just let me check this. Control plus. Okay. For TiO2, we can see affinity is 4.1. Band gap is 3. Let me close this one. Yes, save it. And this is TiO2. The affinity is 4.1. The band gap is, maybe work function is I don't know, we must think about it. Maybe it is band gap and affinity summation. Maybe. Let me try. I just think about this and we'll let you know. So let me switch layout. Okay. The band gap is 3. Okay, there is no narrowing. NC and NV related to MN and MP. It is out of my focus now, but let me check mu n and mu p. Mu n and mu p is about -2 and 2. And 2, okay. And I don't want to use a recombination rate here. Nice, and okay it. I go back to I go to a Spiro method. Spiro, the affinity is 1.9, the band gap is 3. The band gap is 3, 1.9, okay. 3, 1. And the mobility is 2 and 1e minus 2. 2, 1e minus 2. Nice. And recombination, I remove the recombination for now. And for perovskite, let me check the perovskite. It is 1.52. 1.52 and 3.6. Nice. And also epsilon, we could change. Epsilon is 18. Nice. And recombination, I remove recombination for now. The mobility is 2, 2, 2, 2, okay. And I can okay. I just okay this and I just save it, and I recheck the epsilon for TiO2 and Spiro another time. TiO2 is 31. Okay, and Spiro is maybe 3. Yeah, it is 3. It is 3, and I just okay it. Nice. I just save it and I run it again. Okay. Maybe we can work on the mesh, on boundary condition, on electrical condition, work functions, band gaps, and also the defect properties, everything. It needs time. Okay, this is the tutorial video, and you can do everything, and also you can contact with me at any time and you can order your project. If you need any project, I can do that. I will teach you, and please support me by seeing my video multi-time. Share my video to your friends. It helps them. It helps them to understand the basic of the simulation, especially for solar cell or optics and photonics. And I appreciate that. Thank you. Okay, it is running now. In previous running, it was stuck at 400 now, but it is continued. Look at this. This is sensitive to the data. Okay, and now it is running more than 400 millivolt, and it is good news. Nice. It is running now. Still running. Very good. 600 millivolt. Nice. 620. Very good. $700 millivolt. Very nice. 760, 80, 800 millivolt. It's 0.8 volt. Very good. I always insert my numbers and my email address, WhatsApp address, Telegram address in the caption of the video, and you can contact with me. Okay, the final voltage was 840 millivolt. I can quit and save. It means low, higher than maybe open circuit or mesh condition or other thing. Okay, let me check the AU contact current. Nice, you can see the current. Let me remove most of them. IP, okay, IN, I. Nice. We can see the current density, or just current. This is for VFTO contact. Let me check the, excuse me, this is IU contact. We can see also FTO contact, and this is the good result because this is the same as we see in IV curve of solar cell, and we can visualize FTO contact. Okay. Nice. This is for contact. We can remove the label. Okay. This is for VFTO. This is for, that was for AU contact. And we can see this is very low values. Maybe generation is not light for these, but here we added. Oh, look at this. The generation was reading here. It means it's so bad. Maybe let me check the generation rate. Oh, this is generation rate data. Okay, okay. And we can select this model to correct values to collect this together to see the correct IV curves. Okay, but now IV curve is okay, but it is in dark condition. Okay, I hope you enjoyed this video. Please like my videos, share your comments. Please subscribe to my channel. Support me. I'm really near to the monetization, and your subscription, your video watchings help me to get these goals very soon. Please take care. Have a good time. Goodbye.